Welcome to second and mixed partial derivatives. So the idea here, just like we can take sort of repeated derivatives of a single variable function, so just like we can take repeated, derivatives of a single variable function, we can also take sort of repeated derivatives of a multivariable function. So we can also take sort of multiple derivatives of a multivariable function. But now we have the freedom to choose at each stage whether we differentiate with respect to x or y. So we have choice at each stage, which variable we take the partial derivative with respect to. So we get a little notation. So f sub x is the second partial with respect to x. Or the second partial derivative with respect to x. This means we differentiate with respect to x and then differentiate with respect to x again. So we take the partial derivative with respect to x of the partial derivative with respect to x of f. We also have fyy, which is the second partial derivative with respect to y. And then we have fxy and fyx, which are both mixed partial derivatives. And it turns out that as long as we have as long as these are continuous, they're equivalent to each other. So these are equal. It doesn't matter which of the derivatives, which partial you do first and which partial you do second. So just a note, it doesn't matter whether you do, I'm actually going to call this mixed partial derivative, and it doesn't matter whether you differentiate with respect to x or y first. So in your homework, you will actually, or you may show that the mixed partials are the same, whether you do x first or y first. For here, we're just going to operate under this assumption that they're the same. So for our example, let's look at the function f of xy is equal to 3x to the 5th y cubed minus 4x over y. Our job is to find the second partial with respect to x, the second partial with respect to y, and the mixed partial derivative. So first up, we have to find the partial with respect to x and the partial with respect to y. So our first step is to find the partial with respect to x and the partial with respect to y. So we have f of xy is equal to 3x to the 5th y cubed minus 4x over y. For f, the partial with respect to x of xy, the partial with respect to x of f evaluated at xy, we treat y as a constant. The x to the 5th goes to 5x to the 4th. So we have 3 times 5x to the 4th times y cubed. Then the minus 4 over y is a scalar multiple of x. So we just get minus 4 over y. So our partial with respect to x here is 15x to the 4th y cubed minus 4 over y. For our partial with respect to y, three x to the 5th acts like a constant. Y cubed goes to 3y squared. And then the minus 4x is acting like a scalar multiple. We have over y. So that becomes plus 4x over y squared. Derivative of negative 1 over y is a positive 1 over y squared. So we have, therefore, the partial with respect to y is equal to 9x to the 5th y squared plus 4x over y squared. Our next step is to find the second and mixed partials. So step 2, find the second partial with respect to x, the second partial with respect to y, and the mixed partial. So the second partial with respect to x, this we take the partial derivative with respect to x of the first partial with respect to x of f. So we're looking at the partial derivative with respect to x of 15x to the 4th y cubed minus 4 over y. So if we take this partial derivative with respect to x, the first term, we would have a 15 times 4x cubed. That's the power rule on x to the 4th times y cubed. That minus 4 over y has no x's involved whatsoever, and so it's just plus 0. So we get our second partial with respect to x is 60x cubed y cubed. Next up, we take our second partial with respect to y. So this is the partial derivative with respect to y of the first partial with respect to y of f. So we are looking at the partial derivative with respect to y of 9x to the 5th y squared plus 4x over y squared. So if we take this partial derivative, the 9x to the 5th comes along for the ride. Y squared goes to 2y. Then we have a plus 4x that stays. Y to the negative 2 is times a negative 2 over y cubed. So we are looking at 18 x to the 5th y minus 8x over y cubed. Finally, for our mixed partial, fxy, this can be either written as the partial derivative with respect to y of the first partial with respect to x, or you can do the partial with respect to x of the first partial with respect to y. So in this case, we are looking at the partial with respect to y of partial with respect to x was 15x to the 4th y cubed minus 4 over y. If we now take this partial with respect to y, we would have 15x to the 4th comes along for the ride. That y cubed becomes a 3y squared. So we have 15x to the 4th times 3y squared. That minus 4 over y goes to a plus 4 over y squared. So we are looking at 45x to the 4th y squared plus a 4 over y squared. Just for the fun of it, note if we took fyx of xy, the other mixed partial, I claimed these are the same. This is the partial with respect to x of fy of xy. This is the partial with respect to x of our first partial with respect to y was 9x to the 5th y squared plus 4x over y squared. So we have 9x to the 5th y squared plus 4x over y squared. If we take this partial with respect to x, this becomes a 9 times 5x to the 4th times y squared plus a 4 over y squared. Again, that 4 over y squared is acting like a scalar of just x. This, of course, is 45x to the 4th y squared plus 4 over y squared. And that is precisely what we got for fxy of xy. So as I mentioned, these two mixed partials are equivalent. So you can differentiate with respect to either variable first and then switch to the other variable second. The whole way through, I was using this partial derivative notation without actually defining it. So using a lowercase delta instead of a d in our sort of ddx notation, this means a partial derivative. So this is how we can go about taking partial derivatives and second partial derivatives, as well as mixed partial derivatives. And that is pretty much all you need to know about partial derivatives.